Good afternoon, everyone. I'm very glad to share our recent work about the scalability and also security of the cross-chain systems. Okay. So I'm Tian Wei. I'm currently an assistant professor from the CCDS in NTU. All right, let me start with like a brief introduction of blockchain, which is actually clearly very basic for everyone here. So basically, like blockchain has experienced very fast development over the last 2 decades. Okay, it starts with the introduction of the Bitcoin in the year of 2009, and after that we have witnessed different types of the systems and also technologies. For instance, in the year of 2015, we have the Ethereum, which marks the beginning of the mature decentralized applications, also smart contract. And 2 years later, we have the Chainlink, which shows like possibility of building the off-chain network, which we try to offload some computations off the blockchain. And later we have like Terra, which is a mature decentralized finance applications. And then we have like the Cosmos, which shows like it is possible to combine different types of blockchains to get heterogeneous systems for better flexibility. And then in the year of 2020, we also have like a more advanced Solana system, which can enhance the performance and also scalability. Okay, so basically, like the blockchain system, actually has quite a lot of mature applications in addition to the finance, like the cryptocurrency, like the bankings, like the assets management. It can also be used for other purposes, like the healthcare, like the supply chain monitoring, and also manufacturing. Okay. But the blockchain also has some limitations compared to the conventional like the finance systems. So for instance, scalability is always a big concern we need to consider when we try to apply blockchain in our system. So because like we need to build like blockchains across every node, and we need to set the agreements between every nodes, which means that we takes longer time in order to confirm transactions on the chain, and also which means that the transaction throughput system is limited, and also because sometimes, especially for larger scale systems, we have like higher transaction supply demands, which is actually higher than the actual demand, and this mismatch can also cause higher transaction fees. Okay. So here we show some statistics. So the first one is the scalability issues. So basically for the Bitcoin blockchain system, every second we can like create around like 4.5 transactions. This limited by its nature, computation nature. Okay, so this figure shows the number of the transactions created all the time. Okay. And if we switch to the Ethereum, this is better. Okay, we can achieve around like 14 transactions per second. But still, if we compare it to like the conventional like a Visa system, this is far less than the Visa. Okay, right? So like currently for the Visa system, we can handle around like 65,000 transactions per second all over the world. This is much more than the different types of crypto system. And in addition to scalability, okay, the cost expensive problem is also very significant. Okay, so for instance, in order to reach the to approve transactions for Bitcoin, it takes around like $15 in order to finalize a transaction. And for the Ethereum, it takes about $3, which is clearly very expensive, especially if we want to like apply like those crypto solutions in our daily life. Those high transaction fees definitely can be a big drawback. Okay. So this is for like a traditional, like a single chain, and then let's switch our interest to the multi-chain transactions. Multi-chain transaction means that we try to incorporate different types of the blockchains into one ecosystem. Okay, so for instance, like if like two parties wants to make transactions, one party only has account in the Bitcoin, another party only has a account in the Ethereum, and then we have to have such a mechanism or such a solution which is able to make them do the transactions even that belong to different blockchain systems. Okay, so this is called a multi-chain transaction. Okay, multi-chain transaction actually provides us more flexibility. It enables like different blockchains with different features, different security guarantees, different performance requirements to work together to address our demands. Okay, so this is a multi-chain transaction. But a multi-chain transaction actually will be more complex and also more difficult. It actually, the previous problems we mentioned will be more significant in the multi-chain transactions. Okay, so first, the scalability and the cost issues still remain in the multi-chain transaction. And the second, there can also be new features. Okay, as we mentioned, because now we have different blockchain systems, which means that we need like some solutions to do a coordination. Okay, for instance, we need to like some intermediate nodes to coordinate like the actions from different blockchain systems. Okay, and this involves like more communication. Okay, and because we have like cross-chain communication, this can like become a new performance bottleneck. And also, like different chains will have different features, which means that we also need to have a mechanism to make like the interoperability very smooth. Okay, so this also gives us new challenges. Okay, so for instance, like here we give an example of the conventional multi-chain solution. Okay, so the solution is pretty simple. We just introduce intermediate node, like England. Okay, so assume like Alice wants to do the transaction with Bob. Alice is in the Bitcoin and Bob is in the Ethereum. Okay, so they cannot do it simply do the transaction. And then we can introduce a third party, England, which has accounts in both systems. And then Alice can make transaction with Ingrid, and Ingrid can also make transaction on Bob. And then in this case, we can achieve like the transactions across chain transactions. Okay, so this is simple but also naive, but also it has some limitations. For instance, this will fully depends on the England. Okay, the entire mechanism depends on the England. Okay, it requires England to fully be online all the times. Okay, England cannot be offline. If it is offline, and then Alice cannot make transaction with Bob. Okay, and also because like it has higher demands on the England, which means that it will also increase higher agency fees. Otherwise, England will not be willing to be involved in this system. Okay. Okay. So the second issue, as we just mentioned, there will be like the coordination schemes between different systems. Okay. So because we know like different blockchain systems have different features. Like Bitcoin or the Ethereum, they have totally different features. Okay, so we have to have a solution which can be compatible with all different types of features. Okay, existing solutions that try to build a smart contract to do the coordination, but the problem is some contracts may only support the Turing complete features. Okay, like Ethereum. Okay, so if we apply to like the non-Turing complete system like the blockchain, and it will not work. So this also gives us limitation. If it does not work, which means that we are not able to do the verification about the transactions about the blockchain system, which clearly will lose like the assurance on the transactions. This is another challenge we need to address. Okay. So to summarize, okay, in the realization of the multi-chain systems, we have the scalability issue. We have like the transaction fee issue. We also have like the compatibility issue. And what we try to do is to make it more scalable, make it more efficient, and make it more compatible. Okay, so for instance, in order to address scalability issues, we can try to move some transaction operations offline, which will be easier to relieve the burdens of the intermediate nodes. Okay, and also we can reduce the online time of the intermediate nodes, which also can reduce his transaction fee. Okay, so to this end, we introduce our latest work. We call it Site-CVC, which is an efficient and compatible multi-chain virtual channel protocols, okay, in order to address above goals. Okay, so here let me, so this is, the protocol is very complex. We actually develop a lot of mathematical formulas and also secure analysis. But here we do, today I do not want to go through this very boring processes. Here we just use some examples, simple examples to simplify the mechanism, our solution. Okay, so we consider like two parties, Alice and Bob, in different blockchain systems, and they want to make transactions. Okay, so to achieve this, we also introduce a third party, Ingrid, okay, which has accounts on both systems. Okay, so in order to enable the channel, because Alice and Bob, they do not have direct payment channels. Okay, so in order to set up this channel, what we can do is to build a channel between Alice and Ingrid, and also build another channel between Ingrid and Bob, which is actually done in the previous work. Okay, so basically, in order to build a channel, okay, so Alice and Ingrid, for the channel alpha, Alice and Ingrid needs to deposit some money. Okay, so Alice needs to deposit X alpha A, and Ingrid needs to deposit X alpha I to this channel. Okay, to start to open this channel. Okay, at the same time, Ingrid and Bob also need to set up a channel on the other blockchain system, and similarly, they also need to deposit some money in order to open the channel. Bob will be X beta B, and Ingrid will be X beta I. Okay, so this is the initialization in order to open the payment channel. Okay. In addition to the after that, we actually is because with this we actually able to to have like a more virtual channel, because we have the channel between Alice to Ingrid, and we have a channel between Ingrid with Bob, which means that we are able to achieve a virtual channel. This is a virtual channel between Alice and Bob, even that do not have like a direct the ledger channels. Okay, but with the involvement of Ingrid, Alice and Bob finally can do the connections. Okay, so in this virtual channel, Alice actually is required to deposit a certain amount of money. Like we set like this virtual channel as gamma. Okay, so and then Alice needs to deposit a certain amount of money, like X gamma A. Okay, and similarly, Bob also requires to deposit some money, which is X gamma B. Okay, and those money is actually are part of the channel alpha and channel beta, okay, which we did previously, which is actually the actual ledger channels. Okay, so and also because we do not trust anyone, even Ingrid in the system can be malicious. So we also need to ensure that Ingrid is not be able to do any malicious behaviors. Okay, like if we fully trust Ingrid, but if Ingrid is adversary, and then he can totally manipulate the transactions. So in order to achieve this, we also set up a punishment scheme. Okay, which means that if Ingrid did something wrong, he will get punishment. In order to achieve this, Ingrid will also need to set some collateral. Okay, so if he did something wrong, he will lose the money. Okay, so we set a collateral which is 2x gamma I. Okay, so after that we are able to set up this virtual channel between two entities in two different blockchain systems. Okay, so now after that after this the virtual channel is set up, now we can do the transactions. Okay, Alice and Bob can do the transactions. Okay, so what do we do here? The transaction, in order to do the transactions, we actually only need to update the state S in the virtual channel gamma. We do not need to do like the physical transactions like from Alice to Ingrid and to Ingrid to Bob. We only need to do to update the state, the virtual channel state. Okay, so this whole process does not need the involvement of the Ingrid. Ingrid can be totally offline. He does not need to like monitor or does not need to actively participate in these transactions. Okay, so for instance, if Alice wants to pay Bob like two coin. Okay, in this case, we can simply can just reach agreements that the x gamma A will be deducted by 2, and the x gamma B will be added by 2, which means that okay, there is a transaction from Alice to Bob of 2 coins. Okay, and these payments, these transactions can happen. We can have like arbitrary number of transactions. Okay, not just one. Once this virtual channel is opened, we can have like arbitrary number of transactions. Okay, so later like Bob can pay back Alice like 1 coin, and then we just update the state as x gamma A will be deducted by 1, and x gamma B will be added by 1 because Bob pay back Alice 1 coin. Okay. And again, later Alice wants to pay like 4 more coin to Bob. So we deduct 5 from x gamma A and increase 5 from the x gamma B. Okay, so we can do it like not for error. We can do it multiple times before Alice want to finish the session. Okay, so this is actually the advantage of our solution because now we can put Ingrid totally offline. Okay, Ingrid is only involved when we need to open up the channel or when we want to close a channel. But during the transaction, for arbitrary number of transactions, Ingrid does not need to involve, okay, which can definitely be more efficient and also can reduce a transaction, reduce the transaction fees for the Ingrid. Okay. Okay. Right, so finally, if Alice and Bob does not want to continue transaction anymore, and then they can agree to close this virtual channel. Okay, in order to close a virtual channel gamma, and then we finally need to update the states for the actual 2 channels, alpha and beta, on the 2 systems. Okay, so for instance, but finally, if for all the transactions, if we have the state n here, and which means that for channel A, okay, so Alice will lose 5 coins, and Ingrid will have more 5 coins, and in channel beta, Ingrid will lose 5 coins, and Bob will have 5 more coins. Okay, so this is like the update of the 2 states in the 2 channels when Alice and Bob agrees to close the channel. Okay. And also Ingrid will get all his collateral back if he exactly follows the protocols. Okay. So here we just show a case that actually Ingrid does not receive any like the agency fees, but it is also possible that Ingrid will receive more agent fees. In this case, Alice and Bob will pay more to Ingrid. Okay, so so this is like the final state. Okay, so for the alpha state and for beta state, and then we need to do the state update, and then we close 2 channels. Okay, and which means that for the entire process, okay, so the Ingrid only needs to interact with the blockchain twice. Okay, twice, close, open, and close. Okay, and then you can perform like n times of payments. Okay. All right, so yeah, this is what we mentioned here. Okay, and also in order to open and close the cross-chain protocols, in order to close the chains, we need to have a protocol to ensure that every party is exactly following the protocol to make sure that they will not like do any damages or not do any malicious behaviors because we do not trust anyone. Okay, so in this case, we need to have a protocol in order to achieve this. Okay, so the idea is that because now we have 2 blockchain systems and they do not like have information with each other. Blockchain C1 cannot read information from blockchain C2. Blockchain C2 cannot get information from block C1. And then in this case, we need to design a compatible protocol to achieve those like the open and close actions for high security. And we introduce our protocol. We call it Site-CVC. Okay? So it helps like two blockchains to read each other's state in order to verify that each blockchain system is secure. Okay? And here we introduce a new protocol without like a smart contract or other chains, because smart contract, as we just mentioned, it might not support like the non-Turing complete systems. So we just use a protocol instead of blockchain. Okay, so here let me just give like a brief introduction about the mechanism of the protocols. Okay, so basically we introduce like two signatures. We call it signatures, sigma alpha and sigma beta, on the two channels. Okay, so those signatures denote the open and also close the conditions in order to so for all the three parties that agree to open the channel or that agree to close the channel, those are the conditions that need to meet in order to reach agreements. Okay, and in order to do the operations, that must like those conditions are satisfied, they are valid. Okay, so in this case, in order to do any operations, open or the close, Alice and Bob need to send a signature to Ingrid, and then Ingrid will do the verification. Okay, those signatures actually includes like every state, like different states of the two channels, channel alpha and channel beta, and then Ingrid will do the verification. Okay, and at the same time, Ingrid after verify it, it will also like send back some information for Alice and Bob to do the verification to ensure that those the Ingrid's behaviors is also verified. Okay. Yeah, so this is like the other direction that both need to verify with each other. Okay, and this the one big feature of this is that it is actually very compatible with a non-Turing complete blockchains like the Bitcoin. Okay, all right. So as we mentioned that after every time we design a system or protocol, one important thing is to ensure that these are totally secure. Okay, so we need to specify some secure properties our system is able to satisfy. So for instance, every time like when our system opens the virtual channels, we need to ensure that all the parties reach the consensus when open the channel. Similarly, when they close the channel, they also must be agreed by all the parties. Okay, and also we need to ensure the balanced security, which is also basic in the blockchain transactions. No honest parties will like lost its coins, and also nobody can steal like honest parties' coins. These are the basic requirements. Okay, so actually, in order to prove those secure properties, we actually have a very complex modeling and also formal definitions with ideal functionality. So here we define different functionalities for different operations: open the channel, update the channel, close the channel, and also offload the channel. This is too complex. I will just ignore this part. And also, like this is how we do the verification for the open and the close. And we also do the secure analysis based on the universally composable framework. We build a simulator to ensure that all the mentioned security properties are actually satisfied. Okay. All right, to conclude, okay, so in this work, we actually introduce a protocol, Site-CVC, which is able to achieve efficient cross-chain transactions. Okay, it helps us to do the verifications of the different blockchain systems when they are connected together. Okay, and also it will be very efficient for the intermediate nodes because they do not need to stay online all the time. Okay, so it can reduce the number of the on-chain transactions. It can be compatible with like the non-Turing complete blockchain systems. Okay. And we continue our work as in the future. So basically, we try to design the system from different perspectives. We try to enhance the security, which is to minimize the trust parties the parties we trusted, and also we hope to improve the user experience by decreasing the latency, and also like how to reduce the transaction fees, how to extend the the systems, the protocols in more complex scenarios, because sometimes like users may dynamically join the system or dynamic quit the system. This will also need extra support. Okay, and also we hope that our solution will be more universal to support more types of heterogeneous blockchain systems. Okay. Right, that is all I want to share. Okay, thank you.